So, in order to fully understand and appreciate gas laws, in addition to understanding kinetic theory as we described in the previous video, you must have a firm understanding of what pressure is. And the concept of pressure is really pretty simple. You see, kinetic theory tells us that gases are moving particles, freely moving around in linear motion, sustaining numerous collisions with each other and the sides of the wall. So if this is a wall of a container and there's an inbound gas particle, it slams into that wall, and the collision's completely elastic. It bounces off and has the same kinetic energy it had before it collided. But during the point of impact in that collision, it pushes on the wall. It exerts a force on the wall of the container. And of course, numerous gas molecules are doing this all at once, bouncing, exerting force. And so more particles can exert more force, but it also depends on the surface area, how much container wall they're colliding with. And so the pressure of a gas is simply a ratio of the force that these moving particles have when they collide with each other, the walls of the container, etc., and the area of contact of that collision. And so therefore, the greater the force of the particles, the greater the pressure. But the bigger the surface area of the container, there's an inverse relationship, the less the pressure. So yes, if you took the same sample of gas that was in a small container exerting a certain pressure, and you introduced the same amount of gas at the same temperature, so obviously the forces exerted by the gas would be the same, but you introduce to a larger container with a greater surface area, the pressure would drop. There would be a lower pressure. So it's important to remember that pressure is nothing more than a ratio, directly related to the force of the particles when they slam into the container, and indirectly related to the area with which the particles make contact. Now, how do we measure pressure? What units do we use? Well, there's the good old British units used by very few folks other than Americans. But we in America measure our force in pounds of force, and our surface area in square inches. And so pounds per square inch is one way to measure force. We sometimes refer to it as PSI, for pounds per square inch. But if you're going to use the metric system, force is measured in units known as newtons, and this big N stands for newtons. A newton is not a lot of force. It's literally the amount of force necessary to accelerate or increase the motion of a 1 kilogram mass by 1 meter per second squared. And so it's not a lot of force. But the units of area are quite large. A square meter is almost a yard on each side for the area. So a pascal, as it's called, instead of newtons per square meter, we call them pascals, actually is a very small unit of pressure, much smaller than a psi. And so therefore we sometimes use kilopascals when we talk about pressures of gases that are quite high, because pascals are such small units. Now, another way we measure pressure is in what are called atmospheres, abbreviated ATM. And an atmosphere of pressure literally is the pressure that the gas in our atmosphere would exert at 0 degrees Celsius at sea level on a normal pressure day. So it literally is the pressure of the Earth's atmosphere. But the most interesting units of pressure are when we describe pressure using lengths of a column of a liquid. And the most commonly used one is millimeters, thousandths of a meter, not a very long measurement, of mercury. And of course, under most conditions, mercury is a liquid. So how do we actually measure pressure using lengths of a liquid? Well, I'm going to construct a drawing of a crude barometer, something that measures atmospheric pressures. And a barometer would be nothing more than a dish full of liquid. Let's say that it's mercury. and then a tube that's sealed at one end but open at the other end, and the tube is filled with the same liquid that the dish is filled with, in this case mercury. Now, obviously, if this liquid mercury column is supported above the level of mercury in the dish, there is a gravitational weight force that wants to pull it downward so that it leaves the tube. Now, if there's a net downward weight force, all of the mercury should slip down to the same level as the mercury in the dish, and it might even overflow, so to speak. However, it doesn't. Instead, what you see happening is the level of mercury in such a situation, let me get my pen back here, would drop to a certain level, and then it would stop dropping magically. And because it's no longer moving downward, there must be no net force at some point operating on this column of liquid. It still has weight wanting to pull it down, which means there must be a contrary force pushing it up for it to no longer drop despite this weight force. So you have a battle of weight versus mystery force that's pushing the liquid upward. And it's really no mystery. The force that is in fact supporting the column of liquid is the force of the gas in the room. Because let's not forget, it is slamming into everything in its way. And it's slamming into the surface liquid here in the dish and attempting to push the liquid downward. But liquids are not compressible. You can't confine them to a smaller space. So if the gas from all directions pushes the liquid down, it also pushes it up into the tube. And therefore, when the pressure of the gas in the room equals the weight of the column of mercury would stay steady. And we could measure how high the column is, a length of mercury, so to speak. And if you use a mercury barometer, the atmosphere, one atmosphere, can support 760 millimeters of mercury. That's about 3/4 of a meter, 3/4 of a yard if you like British. So not that high a column can be supported, but mercury is very dense and very heavy, so even a column of it that's 760 millimeters high has a significant weight trying to pull it down. So yes, the atmosphere can support it against its own weight. Now, if you used a less dense liquid, we made our barometer out of water, for instance. Water is almost 14 times less dense than mercury. So of course, with the same pressure pushing the water downward, trying to compress it, since the water doesn't weigh anywhere near as much, it could be supported much higher. And in fact, if you can support 760 millimeters of mercury with atmospheric pressure, that means you could also support over 10 meters of water, over 30 feet, a couple of stories of your average building column of water could be supported by atmospheric pressure. And that's why divers know the experience when they go diving. Of course, at the surface, as we're swimming along, we're under 1 atmosphere of pressure. The gas above us is pushing us down. But when we dive down into the water, if we dive down approximately 10 meters, we have this whole column of water piled on us now, pushing down with an atmosphere of pressure, and the gas is pushing down on the water with an atmosphere of pressure. So at 30 feet, you're actually at 2 atmospheres of pressure. You go down even further, 60 feet, you're at 3 atmospheres. At about 100 feet, you're 4 atmospheres of pressure. And so, of course, you get greater and greater pressure. And if you go too deep, then of course even submarines can have their hulls crushed by the external pressure, the weight of all that water pushing down on them. So pressure can be measured in a number of different ways using a number of different units. And to set them all equal to one another, so you get a relative scale of these different units, 1 atmosphere is the equivalent of 14.7 pounds per square inch. So yes, if you had a little square inch area exposed to the atmosphere, it's as if almost 15 pounds of force would be slamming against this area. And both of these are equal to about 101 kilopascals. That's 101,000 pascals. And it's also equal to 760 millimeters of mercury, if you care to use those units. And because all of these different pressure units are equal, you can create conversion factors out of them. For instance, let's say I had a pressure measurement of 2.5 atmospheres. And instead I'd like to know what that measure is in kilopascals. Well, it's a simple one-step conversion. Because 1 atmosphere equals 101 kilopascals, I could place the 1 atmosphere down here so that the units cancel, and the 101 kilopascals up here, and we would multiply it out, and it would come out to approximately 252 kilopascals of pressure. So any two of these 4 unit conversions can be used to convert back and forth.